welcome to an optimization use case as presented in the ultra low power workshop. We have some interesting things for you to report on this. It's basically triggered by the observation that copying data from a CAN chip to internal memory on this SK32K chip is very slow. And we like to understand, okay, what is the problem? What can we do? So first we have a look at what kind of system are we talking about. So what we are actually trying to do is to copy a 64-byte message from a CAN flexible data rate controller to internal SRAM, which takes far more time than expected. So we have an NXP automotive MCU. It's an 80 MHz Cortex-M4F running from flash. We have 64 kilobytes of ECC SRAM. We have 512 kilobytes of ECC flash. We have a code cache of 4 kilobytes. We have this CAN flexible data rate controller. And there's also a hardware crypto block that we are not talking about in this system. So looking from the picture, we have some blocks inside this chip, and we can say, okay, these are the ones that we are looking at, the SRAM and the FD controller. So flexible data rate is an extension of the classical CAN protocol where you only have 8 bytes. This message size is extended, so we can do 64 bytes maximum, and we can also increase the data rate to 8 megabits per second, where the classical CAN tops out at 1 megabit a second. So there is this controller in the chip. It receives a data message, and we want to read out this message and store it into SRAM. So since in this flexible data rate we cannot use direct memory access, we have to write a piece of software to copy the data from this chip to RAM. So originally we have a very simple loop where we take a byte from the controller and put it in RAM and do that, increase the pointers and do it until all the bytes, all the 64 bytes have been transferred. So we have a match between the C code on the left and the generated assembly code on the right, and we can do some calculations on that to figure out, okay, how many cycles does execution of this code actually take. So we add up these things, and we also take into account memory wait states, which means that the flash is not as fast as the processor, so it will have to wait a little bit between accesses, and that is in the formula. So we can see that for the simple thing we end up with some 600 or to 800 cycles, and that's not what we expected. So what we do, effectively we read a message, a byte, we store it to RAM, increment the address, check if we're at the end of the message, and if not, we go back to the start of the loop. Now the interesting question is, how many cycles does it take to store a byte or 16-bit word into SRAM? And the SRAM itself is organized as 32 bits. So the original question might be 1. And if we have this SRAM compared and exacted with embedded control checks, then how long does it take in that case? Now then it gets a little bit more complex because the answer appears to be 3 rather than 1. Now the question is, how did this happen? What is the problem? Then we have to look at how is this memory organized. And then what we see is that for each 32-bit word we have an ECC checksum byte that can tell us whether this data is okay or not. And if we write 32 bits at a time, then we get this byte generated and stored as a single write. But if we update a part of this 32 bits, then we have to read the word first, check that it is correct, replace part of the word, and then write it back together with a new checksum. And that means that that's basically a three-step thing: read, update partially, and write. So that means that accounts for the 3 cycles instead of the single cycle. So if we have this ECC SRAM and we update either a byte or a half word, then we always get 3 cycle access instead of 1 cycle access. So the idea is then that we try to copy words at a time, because if we can do a word at a time, we can still have this single cycle write. So we have a similar loop, but now we write 32 bits at a time instead of just 1 bit at a time. So that is a lot smaller, so we go down to around 130 cycles, because the loop is smaller and all the writes that we do take only 1 cycle instead of 3 cycles. So that helps significantly. We go down to 126 instead of 500 something. So we do 4 bytes at a time, so we have 4 times fewer times through the loop. And also we have a single cycle instead of 3 cycles. So basically we do things 12 times faster. And also we have less overhead. So, but we still have a loop, and this loop has some overhead. We need to increment the pointers, we need to test, we need to branch back, and that can be removed if we basically say, okay, I know we want to read all these words, so if we just do all the stores and the loads together after each one after the other, then we do them all 16 times this statement, and then that's done. And we have no loops. We just do 16 times this simple read-write action. And what we then end up with is 38 if we run the code from SRAM, or 41 cycles if we run the code from Flash. And that's a lot faster than what we used to have, the 500 something. And the compiler actually does very nice with this. So we could of course also try to do the same thing with a memcopy, memory copy function, a default C function. But the performance of that is very dependent on the implementation of memcopy. For instance, if you have the GCC compiler, it will do 1 byte at a time, so it will be slow. But if you have an IR compiler, it has an optimized copy routine that tries to do as many bytes as possible in one go. So that will also be quite okay to use automatically. But both, they have some loop overhead, but it is possible to tell the compiler, unroll this loop, make all the instructions go one after the other, and then there is the same result as when you do it by hand. So yeah, here you can see the results in the different versions. We have initially 653 cycles. The loop is very small itself in code, it's 16 bytes only. But if we use this smart copy function, then we can go down from 653 to 36 cycles at a slight expand of the code. So if you run from Flash, you will get an extra hit, because you have to wait for a read before you can do the next read. The memory is wide on this processor, which means if you do one read, you can read 16 or 8 instructions, 8 or 4 instructions at a time. And if you have sequential code, then you read once, you have to wait 4 cycles or something before you can do the next read. And with one read you can do 4 instructions, so it means that you have to wait a little bit. But in principle, if you have linear code, you can keep on executing and don't notice that you have this latency. That's good. But if you want to go in loop, then there may be a hit. And what's called a prefetch buffer is where you load these instructions that you read all in one go. And if you execute instructions from this buffer, you can do that without any wait states. So then you don't have to have this hit. But that only works for very small loops, 1 or 2 or 3 instructions or something. So as soon as you have to read again in like a next, when the loop is not completely in this buffer, then you get this extra 4 cycle hit. And then it takes a lot longer. So the idea is that if you have a very short thing or doing pure sequential code, then this mechanism helps, as long as you don't loop. So the idea of this system is that you understand this kind of system behavior, check if you have this SRAM with ECC, error correction code, and understand what happens when you do half word or byte access. Before you can read from this memory, you first have to write it to initialize the checksums for all this memory. And you have to do that 32-bit at a time, otherwise you'll get read errors. Check how efficient your copy routines are, so that you can use the most optimal copy routine and reduce your execution time. So it may be that you have to write your own copy routines, which is something that you would need to do if you are in a GCC. And certainly do not assume that the available compiler libraries are optimal or fastest in any way. We managed to get the execution time from 100 to 8 microseconds, which was quite nice to be able to do that. And also, of course, as a result, the energy you use to do this copying also drops by the same factor. So you save 12 times your energy expenditure using all this to get where you want to be. So this concludes the session. I hope you get some idea of the kind of things that we can encounter in embedded systems and how you can get around some of these issues. Thank you very much for watching.